So welcome to the Gemini Center seminar series on quantum computing. Today we have Viroshaan Uthayamoorthy, who will give a presentation of what he has done in his master thesis. He was actually supervised by Jeroen and Franz Fuchs here, and also Alexander and Halvor Nielsen. And he will talk about how you can use machine learning to improve variational algorithms. So Viroshaan, please take it from here.
All right, thank you for the introduction. Yeah, as Franz pointed out, I'll look into how to use traditional classical machine learning to improve variational quantum algorithms. And just a quick thanks to Franz and Jeroen and Alexander and Halvor for supervising me throughout last year. Hold on, there you go. Right, so this is roughly how I have structured today's presentation. Just so that we're all on the same page, I'll start by going over some background information necessary to follow along this presentation. Particularly, I'll be discussing variational quantum algorithms, classical neural networks, and QAOA. From there, I'll be talking about two particular parameter initialization methods for choosing these optimal QAOA parameters. These are called inter and parameter fixing. QAOA is, by the way, just an ansatz, which is essentially like a quantum model of sorts. We'll come back to that, so this will make more sense in a minute. What these two particular methods aims to do, inter and parameter fixing, is to generate good parameters for the QAOA circuit structure that is capable of, in our case, solving the MaxCut problem quite well. So based on these two heuristics, a neural network may be able to learn the parameters of the QAOA parameters to form predictions on new graph instances. This I've tried to illustrate on this figure right here. So you have this traditional feedback loop between a quantum computer and classical optimization. This is just on a regular computer, essentially. And then circuit evaluations cause measurements. These measurements can then be used to calculate some cost. In our case, we'll be calculating the cost function of the MaxCut problem. And then we can optimize these to either find the a local minimum or a local maximum, preferably the global one. And these optimized parameters can then be fed back into the quantum computer, and then we get this feedback loop where we use the quantum computer to perform measurements, which then gives us a rough guidance as to how our cost is. Yeah, and the optimizer then inherently starts to find patterns in the parameters, which we can then use a neural network to learn these patterns and then form parameter predictions, which can then be fed back into the quantum computer, and then we get this sort of a passive use of the neural network. Essentially, we create a data set from this feedback loop, and then based on these data that we have gathered, we can learn the parameters from the neural network. On the other hand, the neural network is more actively used in the second method, where it is essentially used to avoid local minima in VQAs, variational quantum algorithms. So in this setting, we take measurements from the quantum computer, we chuck it through a neural network. These then transforms the measurement. And based on these transformed measurements, we can calculate the cost, and these costs can then be optimized. And then those parameters are naturally fed back into the quantum computer. As you can see, the structures of the neural networks are quite different in these two settings. I'll elaborate more on that as we get there. Right, so to the left here, we have the general structure of variational quantum algorithms. They essentially consist of three parts. First, we have the embedding strategy. Then we have the variational circuit ansatz. And then we also thirdly have the measurement procedure. These are essentially just unitary transformations. They need to be unitary since these are quantum circuits. Although less relevant for our presentation, embedding strategies refers to a way to embed classical data or classical information into qubits. One may, for instance, you do this through basis encoding, essentially naively turning classical bits into qubits, Or we may use amplitude encoding, where information is encoded into the amplitude of the quantum state itself. Very few people have actually tried to use the latter way of encoding information, primarily because we then encode information in a probabilistic way, but it is still possible. And as you then can see, the encoding strategy then depends on X, which is then just the classical data, for instance, a classical bit string. Measurement procedures are also quite important and needs to be included if the measured Hamiltonian is not in the computational basis. This is represented by the unitary M. For instance, if we were to measure in the X basis instead, we would naturally have to do a transformation, which transforms the block sphere of the single qubit from the C-axis, or make the Z and X-axis align. So that transformation and other possible transformations would then be included in this M unitary. Lastly, and most importantly, is the variational circuit ansatz. That's this middle bulk here. These can essentially be defined as a quantum model of sorts. By tuning the parameters that define the circuit ansatz, one tries to approximate the quantum state that solves the problem at hand. Very often it's a minimization problem, then we wish to approximate the quantum state, which minimizes some energy. So after this entire circuit, including embedding, variational circuit, and the measurement unitary, one ends then with a final state. So that would be around here. We would have a final quantum state psi. From this, we would repeatedly perform measurements. And based on these measurements, we can calculate the cost of some function. Just chuck it into a cost function, which then takes, for instance, something in Rn and creates a real number out of it. This real number can then naturally be optimized, where one very often then wants to minimize the cost. This optimization actually happens on a traditional computer, not on a quantum computer. So this here is the quantum computer, and then this happens on the classical computer. These then naturally create new variational parameters, which then are inserted back into the circuit. All right. Oh, sorry. Okay. No. All right. So traditional quantum algorithms, by this I usually refer to algorithms like Shor's algorithm and stuff like that, often require quite deep circuits with several layers in them. However, due to noise in NISQ devices, this is simply infeasible. This is why variational quantum algorithms in particular have grown in popularity in recent years. They essentially exchange having super deep circuits, large circuits, with instead smaller trainable ones, which can then be appropriately used for some application which we want to solve. Lastly, with respect to VQAs, I'll quickly go over some of the problems that have been found with variational quantum algorithms. First is a problem of barren plateaus. This refers to a type of cost landscape that is exponentially flat. This naturally causes difficulties in training. I've tried to represent it here with this image, which is the typical image that is associated with barren plateaus. What this essentially means that if we initialize parameters in the cost landscape, which is illustrated by these dots, very few of them will actually be able to be trained with. For instance, if we were to initialize with these green dots that I'm drawing, these will just have a completely flat structure. You'd have no gradient information, and you'd just essentially be random walking in the close vicinity of the original point. However, if you were to initialize the point closer or within this area, you'd actually be able to train it to reach this then global minimum. What has been found is that we have this barren plateau effect for particular ansatz, and this often appears when we increase the number of qubits, so the problem size, and also that noise is able to actually induce this effect, which is not nice. Second is the non-convexivity of the cost landscape. This essentially means that the cost landscape is littered with a lot of local minima, which I've tried to illustrate with this, right? There's a lot of local minima that you can quite readily get stuck in the cost landscape. This is not necessarily only a feature of variational quantum algorithms. Most people who have done some machine learning are familiar with non-convex optimization landscapes, as most of them are quite non-convex. However, in deep learning, it is found that if you just increase the number of parameters in the model, most of the values of the local minima tend to converge towards the global minima. So just make the, for instance, neural network just deeper, or somehow increase the number of parameters that you optimize with, and you essentially solve this problem to some extent. This is also found in variational quantum algorithms to some extent. However, there's a computational phase transition that happens, where if you're in the under-parameterized regime, the values of the local minima are just terrible. It doesn't really give good solutions to the problem. Whereas if you reach this over-parameterized region by increasing the depth of the circuit gradually, you will then potentially find that the values of the local minima are very close to the global one, which obviously you would like to have. However, the location of this phase transition scales exponentially with the problem size. So you'd have to have a lot of qubits or a lot of parameters effectively to actually find this phase transition. So this points a sort of grim picture for VQAs, where one wishes to increase the depth of the circuit to find these good solutions. However, barren plateau and noise sort of like hinder us in finding this point. All right, let's quickly go over what feedforward neural networks are. This is a form of supervised machine learning method where information is passed layer by layer through the network. The inspiration comes from biology, where the saying neurons that wire together fire together, which essentially means that neurons are dependent on how the neurons prior to it were fired for a particular neuron to be activated. So essentially what this means is if this neuron here were to be fired, it is quite dependent on how these all neurons fired and how they connect to the particular neuron of interest here. The way these neurons are correlated with each other, and so essentially the strength between their connections, are what are trainable in our case. So these weights, WAB and omega IJ, so drawn out here, and although naturally all the gray corresponding lines between the neurons as well. Yeah, a very typical example for a feedforward neural network are the classification of an image, where the number of nodes, so nodes are these circles here, the number of nodes in the input node is the size of the pixels, number of pixels in the image, whereas the size of the output layer, so that is the very last layer from which we form our final predictions, are the number of possible classification that the picture can be. Very commonly, we try to separate a dog from a cat within an image, for instance, then we'd have an output layer consisting of 2 neurons. The phis that I have written out here, so that's this phi, this phi, this phi, and this phi, these are referred to as activation functions. Very common ones are the ReLU, the tangents, hyperbolicus, and sigmoid functions. These are supposed to represent that neurons do fire after a certain threshold has been reached and not prior to that. So for instance, the sigmoid function, it's a mapping between 0 and 1. So it takes a real number and then maps it to between 0 and 1, where 1 represents it's fired and 0 represents that it's not being fired at all. Anyway, let's consider the first term then, phi1 w1 times x. This essentially says how the first hidden layer fires based on the input layer prior to it. X is a vector, W is a matrix where each element are the trainable weights of the neural network, and then phi says how these nodes are actually, whether they are fired or not, right? And phi naturally applies this nonlinear function element-wise in the vector of the hidden layer. This term here, oh, by the way, this F essentially displays the output of the entire model, right? It applies the activation function, and then it applies a matrix W2, and then recursively does so until you reach the innermost input layer. What it essentially says is that it's a mapping from Rn to Rk. N is the number of input nodes in the first input layer, and then K is the number of output nodes in the output layer. That's why it maps from Rn to Rk. These are often trained by using gradient-based methods, for instance, gradient descent. And to use that, we need measure the gradient. These are calculated using backpropagation. Backpropagation is essentially just a way to calculate the derivative with respect to some of these weights. For instance, we have the weights here, WAB. The derivative of the cost with respect to this trainable parameter is given by this term here. I won't go into the details because we are quite short on time already. But essentially, it's just a chain rule applied from the outermost layer to the innermost layer. And by saving the intermediate results throughout, we'll be able to actually calculate this value quite efficiently on traditional computers. All right, let's go into the more quantum aspects of this presentation then. Earlier, I had specified that an ansatz as a layer-wise circuit with changeable parameters, right? These were these unitary U's with these variational parameters theta. Now we can specify what the unitaries are through the lens of the QAOA ansatz. This ansatz is quite specialized and are often applied to approximate optimization algorithms. And the structure of it is shown in the upper right figure here. So that's this figure that I'm referring to. As one sees then, the general green unitaries that are shown earlier 2 slides ago essentially consists of 2 parts. The first part is shown in blue, represents the problem-dependent nature of the ansatz. Namely, it is given by e to the minus I gamma hc, where hc is the problem Hamiltonian being solved. In our case, this is the MaxCut Hamiltonian, which I have presented here, and I will come back to it shortly. Secondly, is a layer filled with X rotation gates applied to all the qubits of the problem. This is quite important for the QAOA ansatz because it has the effect of potentially perturbing the incoming quantum state away from a local minimum if it is actually stuck in one. So that's sort of the effect of the mixer Hamiltonian here. As you might have already seen, these unitaries have 2 free parameters, which are these gammas and these betas. So that's these parameters right here. And they are involved, as you can see, here and here. They essentially refer to how long these unitaries should be applied to an incoming quantum state. These 2 sets of unitaries define a single depth of the quantum circuit. So that's the whole green bulk. That's a single depth. Applying these unitaries multiple times in succession for various lengths often will gradually transform the starting plus state. So that is this, which is just a 0 state with a Hermite gate applied to it, into a state which minimizes, hopefully, at least minimizes the problem Hamiltonian HC. So that's this problem Hamiltonian and is obviously also included in the problem dependent unitary as well. The problem being solved in our case, as I mentioned, is the MaxCut problem. This is defined on a graph. So this is a graph problem from mathematics. So here we'll just shift our focus to this graph right here. The goal of the MaxCut problem is to separate the graph into 2 partitions, such that the weighted edges between the 2 sets of nodes are maximized. That might sound a bit cryptic. An easy way of thinking about the problem is essentially to consider 2 colors. Here I have painted each of the nodes either yellow or blue. One then wishes to paint each of the nodes in the graph in a color such that the edges between the yellow and blue are maximized. So in this case, we would then count up all these black lines. So that would be this one, this one, this one, this one, this one, and this one. Whereas these red lines then are within the same partitions of the graph, since they link yellow with yellow and blue with blue. And as you can then see, we then effectively have two separations in this graph. That would be this inner graph, and then we would have these outer nodes here. Right. So our goal in MaxCut then, from a mathematical standpoint, is to maximize this R. This R refers to the approximation ratio. It is a number between 0 and 1 and says something about how close we are to finding the maximum cut of the graph. So that would be the highest number for HC that is possible in our graph then. Cmax technically needs to be known in advance. That's this denominator here, right? To calculate the approximation ratio. Hence, this formula is only sufficient for graph instances where we already know the answer in advance. The goal effectively then is to maximize this R term to the best of our abilities, i.e. we want to increase the mean Hamiltonian, that is obviously this term. We want to increase this as much as possible. For the problem of MaxCut, the problem Hamiltonian, as I mentioned then, can be represented as this here, where we have these sigma i's and sigma j's. These are just the eigenvalues of the Pauli C operator, hence they have the values either -1 or 1, right? And they actually give the expected behavior of our problem of counting the number of edges between nodes that are within two different partitions of the graph with their corresponding weights. So if two nodes, so obviously the i's and j's run over all the node and all the node combinations within this graph, hence why they run over all edge combinations E. If they are within the same partitions, that means sigma I and sigma j are both -1 or both 1, we see that this term then essentially becomes 0. It cancels, and therefore we don't count that edge. Whereas if they are within opposite partitions, one is either 1 and -1, or the other -1, 1, we would then actually count that edge, right? Because this contribution then is 2. And 2 times a half is 1, so we would actually count that edge and weight it by Wij, which is the weight of the edge between the two. HB here, that's this mixer Hamiltonian, as I referred to earlier. Its function, as I mentioned, is to potentially perturb a quantum state away from a local minimum if the quantum state is stuck in one. Otherwise, if the mixer Hamiltonian was not there, the state could not still be in an eigenstate of the problem Hamiltonian, just with a higher energy than the energy that we are actually interested in finding. The total state after the entire ansatz has been applied is given by this quantum state right here, which is then parameterized by this gamma vector and this beta vector. So as you can see, this would then be the pth unitary, and then this would then be the first unitary that we apply, right? So this corresponds to this, and this last one corresponds to this unitary. And then we apply this unitary potentially p times. And lastly, with this box right here, I have shown how the quantum circuit actually looks like for our particular problem. The blue in this corresponds to this unitary, and the yellow corresponds to the yellow, the orange to the orange, and then this plus state that we get initially start with, it is given by 0 and the set of Hadamard gates that we apply to it. What we then see is that this is, by the way, for only depth p equals 1. So we only apply it once, this set of unitaries. Then we will get this probability distribution over all the computational basis states. If we then perform this or repeat this 5 times, we see that the correct solutions, of which there are 6, are properly amplified. And those are the only solutions that we would then get from the quantum circuit. This is, by the way, the graph instance that we use to calculate this or get these probability distributions. Right. Another problem is obviously how do we actually find good parameters gamma and beta such that this approximation ratio is maximized. We investigated two such methods, interp and the parameter fixing methods. Zhu et al. Through extensive numerical simulations find that there's a linear dependence actually between each of the gamma and beta parameters. If one fixes this circuit depth P, so that's the depth of the circuit, the number of gammas that we have in our case, the authors find that the gamma I tend to increase with angle index I, while beta I tends to decrease. So if we have a depth P equals 9 circuit, we would evidently then have a gamma 1 and then up to gamma 9 circuits, as evident by this figure, right? So here P is 9, then we will have 9 repetitions of this unitary. This is what I've tried to plot here. We see that there is this trend of increasing gammas and similarly decreasing gammas. What Zhu et al. Then proposed, and it's a heuristic, evidently, it's not necessarily proven to work, is that we try to exploit this trend when we go from depth P over to depth P plus 1. So we iteratively increase the depth of the circuit. And we want to increase the depth because that often corresponds with better solution to the MaxCut problem. What we then do is that we separate the line from 1 to 9 into 10 and then interpolate linearly to 10 points instead of having 9 points there, essentially. We don't have this underlying blue line here. We only have the points, so we interpolate based on those. And very similarly, parameter fixing heuristic works by finding the optimal parameters at depth P. We generate then 2 new points at random, and then optimize those points, those 2 P plus 1 new parameters, and do this 20 times to find whichever of the 20 parameter configuration gave us the best solution. Okay, and here are some of the findings or some of the trends that we captured. Firstly, looking at the approximation ratio here, we see that it is monotonically increasing with increasing QAOA depth. That's a good thing. We want it to be as close to 1 as possible, which we see happens for 6, 8, 10, 12, and 14 node graphs. These are all unweighted, by the way, and each nodes have 3 neighbors. Secondly is this. Here we see 2 particular trends that Zhu et al. Talked about, with the which the interp heuristic is based on. Firstly, the gamma I tend to increase, as seen here, and then the beta I tends to decrease. So this is what the interp heuristic is based on, and then if we were to interpolate it further, we will just separate the 10 to an 11, generate new points, and then perform an optimization run at that. Then another interesting notion here is to see how do the parameters actually move in parameter space as we increase the depth of the circuit. So the depth of the circuit is plotted along the X line for these. This is the gamma and this is the beta parameters I at each depth P. So what we see here is, for instance, with depth 5, we see that there are 5 gamma parameters and 5 beta parameters. What the parameter fixing method is based on is the notion that the parameters tend to remain relatively fixed when we introduce new when we increase the depth of the circuit, right? At least with the beta parameters, this is most evident. You see that all the parameters tend to plateau and only the newly introduced ones tend to change significantly. So that's why you sort of fix. So as we introduced here, you sort of fix the new parameters and generate only 2 new parameters at each new depth before you actually perform the optimization over the 2 P plus 1 new parameters. And some of the justification for this can be seen in the cost landscape as well. What we here see is if we fix the minima, by the way, now I've turned the maximization problem into a minimization problem. So the minima here gives very good results and the maximum gives very poor results. When we fix the minimum, here I've plotted gamma 1 and beta 1 at depth P1, and here we see I've plotted gamma 2 and beta 2, whilst letting the gamma 1 and beta 1 at depth equals 2 be fixed to this value. So that will be this gamma 1 and then this beta 1. We see that these minima lines tend to emerge in the landscape. And even if we repeatedly keep fixing it, we see that this line then tend to remain, which might then potentially be able to explain why this method performs as well as it does. Whereas if we fix it to a maximum, which is a not good point at all, we see the emergence of like more local minimum, which the procedure could potentially get stuck in. And the value of this minimum is obviously quite significantly worse than this value, for instance. Yeah. Now we are already a bit short on time, but I'll quickly go over one of the ways, at least, we use neural networks to find the optimal parameters. So we use the neural networks to generate two P new parameters. And based on the inter method, I essentially created a data set of graph instances where QAOA was applied to the MaxCut problem. Based on these graph instances, a neural network with 2 input parameters was used to predict all the 2P final depth parameters. And these are the two parameters that are used for the P equals 1 depth QAOA problem. So in the previous picture, that would then be, for instance, these parameters right here. These would then be the input to the neural network. And then based on these, I want to essentially form predictions for all the 10 parameters that are in this level of QAOA depth, right? And what we essentially wish for the neural network to capture are 2 patterns in particular, is this one, where as if you fix the depth P, the angle index tend to increase for the gammas and then decrease for the betas. That's the first trend. And that's the one we discussed earlier, which was the heuristic was based on. And then the angle index tends to, or the gamma I, for instance, gamma 1, tends to decrease if we increase the depth. So this is the depth, right? P1, 2, 3, 4. We then see that the angle index or gamma for a fixed angle index I tends to decrease. So that would then be gamma 1 at P equals 1 versus then gamma 1 at P equals 10. This one would then be lower than this one. Does that make sense? And evidently the opposite happens for the beta angles as well. The justification for using only these 2 features to form predictions for all the 2P final outputs comes from these correlations. And what we see here is that there are some strong positive and negative correlations between some of the inputs and some of the outputs. However, as the depth or as the angle index increases, the correlations weaken. So this procedure is not as effective, particularly for the beta predictions, actually. As you can see, these predictors then tend to decrease quite rapidly, and therefore the predictions are quite good around here, but then they sort of taper off and become quite error prone with higher indices. Beta. Right, so now we'll lastly go over to some of the main bulk of the master thesis here, where we use neural networks to escape local minima. In this procedure, we essentially transform the entire cost landscape using a neural network once the variational parameters are stuck in a local minimum. We're still solving the MaxCut problem using the QAOA structure, so the U's are still the same as I presented before in the QAOA slides. However, the goal is now to get unstuck once we are stuck in a local minimum. And the way we do this is to essentially transform the entire landscape by introducing these extra parameters in the form of this neural network at the end of the measurements. So the measurement bit strings are then the input to the neural network, which we then process, and then optimize with respect to. So we then optimize both theta and the neural network parameters in a stepwise fashion. The neural network function can be is given by this. This is the one we tested out. What this essentially does is it applies the tangent hyperbolicus function to the weights. So the input of the neural network is a bit strings of zeros and ones. So that's 0, 1, 0, 0, 1, for instance. And then we type 2x minus 1 on it to map it to the -1, 1 regime, which is nice because that's, if you remember back to the cost function of the MaxCut, that's the numbers we need to actually calculate these numbers. Then we take multiply it by the neural network weights, Wij, and then perform the tangent hyperbolicus after that. So that's the nonlinear transformation that we actually do with this particular neural network. And we chose tangential hyperbolicus because it ranges between -1 and 1, right? We have this function, we have -1 here and 1 here. And then I actually also perform a sine function at the end just to sort of stick it to 1 and -1 afterwards. As you can see, the cost function here is just the weighted sum of all possible bit string configurations for the number of qubits that we have here. So we have here n qubits, and then here the sum of all possible zeros and one combinations in that. And p of x given theta, obviously the probability distribution of all the measurement outcomes is quite dependent on the parameters theta here. By this term, it is the projection of the quantum state psi down onto each of the computational basis states x. And then naturally we could calculate the cost right afterwards. However, we perform this nonlinear transformation through the neural network, which is why we have this f as well in the argument of the cost function. The cost function is still the same that we considered earlier. We can recall back to that. Let's now quickly go over each of the steps of the procedure. One essentially starts by initializing the weights of the neural network to the identity transformation. So at this point, it essentially does nothing. We just have a VQA problem, perform optimization, and then get some optimal theta parameters, which is then within a local minimum. Once this local minimum is reached, fix the parameters theta and use the quantum computer essentially as a sample generator and train the neural network weights W. When we fix the variational parameters, you can change them now. And then by running this circuit multiple times, we get these measurement outcomes, essentially a data set that we can train the variational parameters on. The variational parameters in the neural network, sorry. Then fix the weights after that, and then for large T steps, gradually alter the neural network contribution and perform update steps for theta. What we essentially mean here is that we alter the neural network gradually from the very changed neural network altered landscape into this landscape that is quite similar to the original one, right? Because this G of T term will gradually approach the identity transformation. And we tried two functions here, T over T, that's this one. And then we also tried the Heaviside function, which essentially just lets you train in the quite altered landscape of the neural network. Yeah, and when plotted with respect to the variational QAOA parameters, the entire cost landscape changes at each time step T. Because we are only looking at it from the lens of the variational parameters, but we obviously have these changeable ones as well through the neural network, which comes in since we post-process the information after the measurements. Yeah. How much time do we have left now, Hans?
Minus 12 minutes.
Oh, sorry. Okay. Maybe we should then skip some of these toy examples and then look at the procedure applied to the QAOA landscape instead. So what we initially have is this green line, which is the initial minimization. note here that blue regions correspond to good regions in cost, and then red to quite worse. What we then see is initially it is stuck in a local minimum. This landscape here is the traditional just VQA, QAOA landscape. And we see that the green then first converges into a local minimum, and then the entire landscape itself gradually changes with each time step t. And at each time step, the parameter vector tends to remain stuck within this local minimum, this attractive basin. And then here happens a quite sharp transition. And then from here to here, and then you see that it then gradually approaches the global minimum of the QAOA landscape. And here we are back to the original landscape. The neural network only applies the identity transformation. And then we just can perform a final optimization just to get stuck in the global minimum. Okay, I think that about covers it. And then obviously we have the 20 examples where we drop that since we are already over time.
Yeah, thank you very much. I think we have time for one quick question if there is one.
Stop sharing. And
if not, then I think thank you for this time, and see you in 1 month next month.